Hi everybody! Today we are doing hot air balloons. Thank you, Jessica, wherever you are, for suggesting hot air balloons. It was a brilliant idea. Look how beautiful they are. They're absolutely massive. When you see them in the sky, I don't think you appreciate how massive they are. Look, that's obviously a person, and that's one that hasn't even inflated yet. They just look really small in the sky, but look, that's a person, and that's how much fire goes into a hot air balloon. We're going to talk about things that you don't think are related to hot air balloons. Have you ever been in the shallow end of a swimming pool? You might have noticed that it's much easier to do things than it is if you're standing on land. Like you can like moonwalk. If you're brave, you can even do handstands, and it all just feels a bit easier. It's like you weigh less, isn't it? Except none of the bits of your body have fallen off. Why would you weigh less? But just think about that. We will get to the bottom of that later. For now, I think we'll just launch straight into story time. 2,300 years ago, the King of Sicily is very excited. He's going to treat himself to a new crown. He's got a solid gold block. Let's say it weighs 1 kilogram. And he gives it to a goldsmith who promises that he will melt it down and turn it into a beautiful crown. But when the goldsmith arrives with the crown, the King of Sicily can't put his finger on it, but something's just not quite right with the crown. The king is suspicious. The gold block weighed 1 kilogram, this crown weighs 1 kilogram. It's the same colour, it even feels the same, but the king suspects that the goldsmith is a crook. He thinks the goldsmith has taken a little bit of that gold brick for himself, and he's replaced it with a little bit of silver that weighs the same, and he's put this cheapo silver in the crown instead. But the King of Sicily's problem is, how is he going to prove it? He doesn't want to destroy the crown, because what if the crown is solid gold? Then he'd have just destroyed a solid gold crown. He doesn't want to accuse the goldsmith, because if he's wrong, that'd be really embarrassing. Oh, he's all in a flutter. And then he decides he'll take the crown to one of the most famous, hard-working, deep-thinking astronomers, scientists, mathematicians that the world has ever known. And we will meet that person at the end of the lesson, and you will find out how the King of Sicily solved his problem. But we'll get back to hot air balloons for now. My question is then, why do hot air balloons go up? To start thinking about it, I have a picture here which I drew for Evelyn. Evelyn really likes giraffes. Evelyn, I'm so sorry, look, I drew these guys before realising that giraffes aren't really orange, are they? They're yellow. I can't believe I've taught you lot a whole lesson on animals. That's embarrassing. Imagine all the giraffes were just relaxing, chilling, whatever, in the field, and then someone lit a fire in the middle of the field. Now, what happened to the giraffes? They got a lot of energy, they started moving around a lot more, they started bumping into the walls of their container a lot more, and some of them even managed to escape. Very, very similar with air particles. We've looked at this before. When air particles get hot, they spread out, they move around. But these giraffes are doing something that an air particle would never do. So let's do our craft. If you're going to do this along with me now, you will need a pair of scissors, pen, a piece of thin cardboard like cereal packet, or piece of paper is fine, and some string. I said thin cotton is better, it is, but if you've got some string, that's fine as well. And a candle in a jar. Tea light is fine. I would like you to draw a circle on your piece of paper or your piece of card. We're going to make like a kind of snaky thing. So once you've drawn your circle, put your pen in the middle and draw quite a big spiral so that it looks like a snail shell. It doesn't have to be very good, which is lucky because mine is very uneven, but something like that. And then cut around that. There we go. I could do shout-outs now while I'm doing this, but you probably can't type because you're all busy cutting out spirals. I want to do a shout-out to Winnie and Joe. Winnie showed me at the weekend that she had made a ball which bounces, which was made of crystals, which also glowed in the dark. A productive weekend, well done you. Joe, I think you were poorly, so I hope you get well soon. Just cutting out this spiral. There we go. Also, it just occurred to me that there's probably a lot of you watching this on your own because your poor parents have to work, and you maybe can't type on the computer, thank you very much for joining me. You are doing an amazing job. So maybe you can't do experiments, but this is why I do them too, so you can do it with me. So I've got something that looks like that now. You will need a grown-up for this bit because you're going to poke a hole, probably with a pair of scissors, into the very middle of the top bit of the snake. Sophia in West Sussex, hello. Okay, we've got a hole in there, and then if you've got some thread, poke your thread through and tighten a little knot. Alright, if you've got your candle in a jar, let's light it and let's see what happens. I've gone through so many matches this week, I've got to be careful because of trying that tea bag experiment again and again and again. I did get a tea bag to fly though. Excited to show you later. Okay, so you've got your candle in a jar because we're going to dangle paper over fire, which you have to be a very good scientist to know isn't a brilliant idea. So you should have something that looks a bit like this. Now just hold it just normally, don't put it anywhere near the candle, just hold it, and this is called observation. Just look at it and say what is happening. Not very much. And then eventually, if you've got one going, you've probably already done this, hang it over the flame. Oh look, there it goes. I've got it in just the right place. You should get it to spin round and round. So why is it spinning? Why do they go round and round and round? Why did that happen? Why? When air particles get more energy, they move around, they spread out, they bash into things. What do they not do? They don't move down. These giraffes have just moved away from the fire in all different directions, but an air particle would never ever ever go down. It would always go up. To really get to the bottom of why hot air rises, hot air does rise, but why does it rise? We're going to look at density. If you've ever been trick-or-treating with a group of friends and you've knocked on the door and someone's appeared with a bucket and shouted, it's two per child, it's two per child, it's two per child, as you all like run forward, I think you would know that it means each child gets 2 sweets. That is essentially what density is. It's amount of stuff per space. So I've got my little blackboard now, and instead of people, we'll do squares. We'll stick with sweets because I've got loads of Parma violets left over from Halloween. No one likes Parma violets. Let's turn you around. Same thing, but instead of people, we'll use squares. So let's say it's 1 sweet per child. Let's say these squares are a metre square. They're not, but it's just much easier to say a metre. There we go. So we've got squares that are a metre up and a metre across, so they're metre squares. So these squares have both got the same density because they've both got 1 packet of sweets per metre square. Let's say these packets of sweets are both 1 gram. So they're both, the density of these squares is 1 gram per metre square. So what's the density of these squares? That's right, it is 2 grams per metre square. Right, so let's see if you've understood. Which of these squares is the densest? Which of these squares is the densest? Yeah, it's this one, because the density of this square is 2 grams per metre square, but the density of this square is 3 grams per metre square. Let's do something a bit tricksy and see if you get this. So I'm going to draw a square which is 2 metres across by 2 metres across now. Let's rub these bits out in the middle. So this square is 2 metres across by 2 metres across, but you can see that it's the same size as 4 squares all put together. Right, which one of those is the densest? Is it number 1 or is it number 2? Which one is the densest? Which one is the densest? Well, here we've got 1 gram per metre square, and here we've got 1 gram per 4 metres square, because there's 4 metres square there and only 1 there. So this one is the densest. If we wanted to, well, I'm holding my, oh yeah, there you go, look, Parma violets. So rubbish, I can break them apart with 1 hand. Oh, there you go, look at that. So here there's 1 whole packet of sweets per metre square. Here there's only like 3 sweets per metre square, so it's not as dense. What about this? Which one of these squares is the densest? Number 1 or number 2? Which square is the densest? So this is 1 metre square, this is 4 metres square. Kathy is saying equal. You're right. Well done. Yeah, it was a bit of a trick. So there's 1 packet of sweets per metre square there. But actually, there's 1 packet of sweets per metre square as well, because it's like 4 metres squared just stuck together. So yeah, well done. If you thought about that the whole time and didn't just give up and think, oh, I'll wait until she tells me the answer, then very, very well done. You have got mad skills, which will take you far. And we use density. Pop you back with me. Density is quite useful. You might have heard like cities and towns described by their population density, and it just means how many people are living per space. So the population density of London is 4,500 people per square kilometre. So if you imagine a much, much bigger square, in London, on average, there are 4,500 people living inside 1 kilometre square. In Manila, in the Philippines, which is the most densely populated place in the world, it's 41,500 people in 1 square kilometre. So if you've ever been to London, you'll have noticed that London is busy. London is really busy, but when you're in a square kilometre, on average, there's only 4,500 people there with you. In Manila, it would be 41,500 people. So that's why density is quite useful. Oh yeah, I thought this was quite an interesting thing as well. If you've ever been to the supermarket, so I've got 2 jars here that are exactly the same. You can see they're made by the same company, they're the same size, exactly the same size. They cost the same, I think. But if you look on the back, I know this is backwards for you, sorry. One weighs 15 grams and one weighs 55 grams. What's happened there? Why are they both exactly the same, except this one weighs 15 grams and this one weighs 55 grams? Well, the answer is that this one, the stuff in this one, the mustard seeds, are a lot denser. Their particles are a lot closer together. So you can fit more stuff in this one because the particles are close together. This one, mint, obviously mint is not as dense. The particles in mint are much more spread out, so you can't get as much in this container. Rach, but they're the same. Well, they're the same volume. You would say they're the same volume because volume is a posh word for space. They fill the same amount of space, but they don't weigh the same because you can get more of the mustard seeds in than you can the mint. Alright, so what's density got to do with hot air balloons? Well, density has a lot to do with how stuff floats. And the science of how stuff floats is exactly the same if you're talking about liquids or if you're talking about gases. But it's much easier to look at stuff that floats in liquids, really. We're going to do a little game called, don't get too excited, Does It Float? Got some fruits here. Just going to put some fruit in a bowl and you're going to tell me if it floats. Oh, good, someone's saying because they're heavier. Yeah, so heavier means weighs more. This is why density is important, because stuff that weighs more isn't necessarily the stuff that's going to float or sink. Like, I think it was World War II, when metal was really scarce, they actually made boats out of concrete. Concrete, very, very heavy, weighs a lot, but because of the way they made the concrete boats floated. Okay, who was at my planets lesson? Is this banana going to float? Just say yes or no. Is this banana going to float? Were you at my planets lesson? Yeah, banana, same as Saturn, does float. Well done, if you said that. Let's peel it, because I'm always hungry after these lessons. Is a peeled banana going to float, or is it going to sink? Sink or float? Come on. Emily thinks they will all float. Okay, that's useful. Is a peeled banana going to sink or float? It is also going to float. Well done if you said that. Emma, science is the best. Science with food is the absolute best. Right, orange. Is the orange going to float? Yes, says Anna. Let's have a look. Yes. We're going to give that a yes. You see the bottom of the bowl? Yeah, it's floating. Interesting, says Sarah. Sounds like Sarah's reserving judgment, and I don't blame you, Sarah. We'll see if it's interesting at the end. Lemon, sink or float? We're just going to go with float. All fruits float today. David says sink. Thank you, David, for being a bit different. Ah, sorry, David, it floats. Blech. Boring. Michelle, a lemon floats, so surely a lime's going to float. Oh, yeah, some of them do sink actually. It's more impressive if they sink. Well, then I don't know what's going to happen here. I've peeled my orange. Remember the orange with the skin on it floated. Is this peeled orange going to float? It sinks! Look at that! And it definitely sunk. There you go. Ta-da! What's that about? So people who are saying heavier and lighter, this is why it's not quite right to talk about things being heavy or light, because an orange with its peel on is more stuff. So an orange with its peel on definitely weighs more than an orange without its peel on. But the orange with the peel on floats and the orange without the peel on sinks. This is where density comes in. And this is where, you remember in our story time, I said that there was a really clever person who we were going to meet who worked out the problem of the crown. He said that whether something floats or sinks or not depends on how many water particles it pushes out of the way. What you can imagine is that with its peel on, the orange is wearing a little life jacket. So if you put a life jacket on, you weigh a bit more because you've got the weight of the jacket on you, but you float, don't you? And it's because the jacket has a very, very low density. And things that are less dense than water float, and things that are more dense than water sink. So because you've put on something that's really not very dense at all, your average overall density is less than the water, so you float. It's the same with the orange. The peel is really not very dense at all. So when the peel is on the orange, overall the density of the orange is less. So it floats. I'll show you what I mean. Yeah, I'll show you what I mean with this. So here are some air particles floating in the air. A basket of a hot air balloon is pretty heavy, isn't it? So a balloon is pretty heavy. It's got a lot of weight. It's got a lot of weight pulling it downwards. If you only use a small hot air balloon, then imagine that hot air balloon has got to push some air particles out of the way, hasn't it, in order to be there. So that hot air balloon, let's say that's pushing away like 4 air particles. Now, those 4 air particles, their weight is pushing the balloon upwards, so that balloon isn't going to go up. That's why balloons are really, really, really massive. They've got to take up a lot of space. They've got to push a lot of air particles out of the way. This balloon has pushed a lot more air particles out of the way, so the weight of those air particles pushes up on the balloon, and the balloon goes up. Basically, if a hot air balloon is going to go up, then it needs to be less dense than the air, which is why you heat up the air inside, but it also needs to be big enough that it pushes aside enough air particles that the weight of those air particles is enough to beat the weight of the balloon. Oh, Phil, a question from Aubrey. Are humans more dense than water? We float, don't we? Oh, what a great question. Have you noticed that if you're lying in the bath and you do a big breath out, you sink, and if you take a big breath in, then you rise? That's because air is going into your lungs, and air is a lot less dense than water. So it's kind of like putting a life jacket on, but inside your lungs. If you've got lungs full of air, then your overall density, overall the particles in your body are more spread out for the space that you take up. So you rise. I was going to say bones are denser than water. Maybe they're not. You'd have to get a bone and float it in water, but don't tell anyone that I suggested that you should do that. Let's leave density alone for now. And I'm going to get you to do a little thing at home if you've got a candle in a jar. If not, then don't worry. Another bit of the hot air balloon that I thought was a bit weird. This is the bit where the flame comes out. Have you noticed that that bit is quite far below the hot air balloon? Surely it would be better if that was in the hot air balloon, because then there wouldn't be any heat wasted like out here. All the air inside the balloon would get hotter, and it would probably get hotter faster. So the balloon would go up. So why is that dangling out there? Well, you could do a little thing at home. If you've got a candle in a jar. Dylan and Riley, that is excellent thinking. Yes, it might set the hot air balloon on fire. Yeah. Right. Robin says, will not burn. Well, let's try it. So, hold the jar above your flame. This candle is burning oxygen. So we're making the air in this jar rise, and you should see... Oh, maybe you can't see. Just going to put it down, and there's just a spot where the flame goes out, but it's still quite a way above the desk. So see if you can find at what spot your candle goes out. But yeah, that's why. Well done, you lot. That's why the fire isn't right up inside the balloon, because oh, it's come back again. Look at that. Hey, that's good. Oh, have a little play with that. It's gone. Yeah, because the air that's sort of being burned, that's being used, that doesn't have any oxygen in it, is all floating to the top and floating to the top and floating to the top, and eventually the whole jar is full of air that doesn't have any oxygen in it, and there's no room for any more air to get in through here, so that's why. Oh yes, you know what it's time for? It's time for the tea bag burning experiment. We're going to burn a tea bag, go back to story time and find out what happened, and that's going to be the end of the lesson. So, these tea bags are Tesco tea bags. If you want to do this at home later, I found that these ones and these ones behave the same way. On their own, I couldn't get it to work. So the tea bag burning experiment says you just open out a tea bag. So you've got a tube of very thin paper like that. And the internet is full of people on YouTube who are just standing up their tea bag like that, lighting the top of it, and the tea bag burns and then flies off into the air. I have not been able to get that to work until, after a lot of playing around, I worked out that the ratios of this tea bag weren't quite right. If you fold your tea bag into thirds, so sort of fold it up and then fold it across again, and then you cut it, then we should see that it flies. I'll do all three. We'll make it a proper science experiment. So that is 2/3 of one of these tea bags. This is a whole tea bag, and this is the little third. That's one. That's two. See? Let's see. Hey, look at that! So the one that's a third floats. The one that was a full one floated. Oh, this one went out. Oh, that's disappointing, isn't it? Yay! Rebecca, I can't get builders' tea bags to do it at all. I've tried everything. If it's one of those like folded up ones with a bit of string, then it usually works. Okay, right. We'll just have the end of story time, and then that is the end of the hot air balloon lesson. Except I hope you've realised the answer to the question about why it's like you weigh less in a swimming pool. You sort of do weigh less because the weight of your body, of gravity pulling you down, is the same. You weigh the same, but you've moved some water particles out of the way, and those water particles, the weight of those water particles is pushing upon you. So you've sort of lost the weight that is equal to the water particles that you've pushed to one side. And the person who discovered that is the person who we are about to meet. You remember where we were? The King of Sicily. He's got this crown. He doesn't think it's pure gold. He thinks he's been swindled. So he flies off to see a person called Archimedes and explains the problem. And Archimedes thinks, oh my goodness, I don't know about this one. There's no easy solution to this, Your Highness. And the king says, well, you know, if you could ponder it, then that would be great because I'm the king. I'm very important, right? Archimedes doesn't know, but he's not the most successful mathematician, scientist, astronomer in the world for nothing. He doesn't give up, he thinks and 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 he thinks. And that night, it's his bath time, and he's still thinking about it, and he just can't work it out. He gets into the bath, and as usual, as I'm sure happens in your bath, as he gets into the bath, the water in the bath goes up as he gets in. And this gives Archimedes an idea. This gives Archimedes an idea so good that as the story goes, famously, he shouts, "Eureka!" which is Greek for "I've got it," and runs naked out of the bath and down the street. What has Archimedes discovered? Well, what he's thought of is the fact that silver is less dense than gold. Here we are. Even though the crown and a gold bar both weigh 1 kilogram, Archimedes has realised that because silver is less dense, the particles in it are more spread out, if the crown has got any silver in it, then it will be taking up more space than a normal 1 kilogram gold bar. Now, how would you measure whether that is taking up more space than that? Well, you could put them both into water, just like Archimedes getting into his bath. With the king watching on, Archimedes puts the crown and an identical gold bar, 1 kilogram gold bar, into 2 buckets of water, and lo and behold, the gold bar, as expected, pushes some of the water up because it's taking up the space that those water particles were taking up in the bucket, but the crown pushes more water up. The crown takes up more space in the bucket, and there you go. The king has his proof that the goldsmith was a cheat and a thief. Hooray! Well done, Archimedes. Well done. That's the end of story time, and that is the end of our lesson. Thank you so much for joining me. At this point, I usually say, please subscribe to my YouTube channel and please like my Facebook page. I've got another thing to say today. We're moving to YouTube. We've got enough subscribers that we're going over to YouTube and doing this live on YouTube from now on. So it'll be the same time. There's no activity sheet this week because I've been writing a recipe book for you, because I've sort of got a proposition for how we make lessons work in the future. Will your cookbook be scientifically good? Yeah, it is. It's a bit sciencey. It's got my favourite recipes in it, and it's got a little bit of science on each of my recipes. Oh, Danny, can you donate for these lessons? Is there a link? That is really lovely of you to say. We should mention that when there are like another 140 people watching. Yeah, there is actually. In the About section of my Facebook page, there's a link to PayPal. Thank you so much for asking. Patreon is a thing. Have you heard of Patreon? It's basically asking people to pay for stuff that they can get for free anyway. You wouldn't think it'd work, but apparently a lot of people do it. So I'm going to try it, and I don't need to make a lot of money. I don't need to make like a wage. It just needs to be sort of able to justify me doing this every week, because I have a lot of fun, but obviously there's a lot of planning. A bit disappointed that my lime floated. Right, finished my banana. But thank you for hanging around with me and let me wind down. That was really lovely. I'll see you very soon. Bye.